and Gareth will talk about evidence for gaseous halos around AGN at cosmic noon from ALMA CO322 observations.
Well, thank you. And thanks to the organizers for setting this up. This has been a really exciting day so far. It's just beginning this week. So I'm Gareth. I'm a postdoc from Cambridge, and I'm going to talk about some work that we've been doing for the past few months, looking at AGN around redshift 2 to 2.5 in CO. So first of all, we should talk about what a gaseous halo is. And we can do this by looking at this cartoon, which is very similar to the one that Ivana showed this morning, except we'll be looking outwards instead of inwards. So we have stars and gas, H2 and H1, that are inside the galaxy. And all of the gas and dust that's in the galaxy, we call the ISM, or the interstellar medium. And this only extends to 5 or 10 kiloparsecs, maybe, from the center. But this galaxy is surrounded by a whole bunch of diffuse gas that extends out to much larger radii. We call this the circumgalactic medium, or CGM. And the CGM is separate from the inner galaxy, but it is still pretty crucial to study since it acts as a gaseous reservoir. The gas in the CGM could fall into the inner galaxy via filaments, or if there's some sort of gravitational interaction or merger, it could also fall into the galaxy and be fuel for future star formation. It also acts as a fossil record for past outflows. Since if we look at the CGM and we see evidence for enrichment, a lot of metals, then these metals must have been ejected from the galaxy via starburst or AGN-driven outflows in the past. We can't talk about the CGM without looking at this really nice watercolor painting. So this is just another view where you can see that the inner galaxy with the stars and the ISM is encased within the CGM, but interacts via inflows and outflows. So these are nice cartoons, but the question is, what does this look like in real life? And there have been a whole lot of studies that have looked at the CGM, especially with Lyman alpha. People have detected Lyman alpha halos that have been hundreds of kiloparsecs wide. But today, since this is an ALMA conference, I'll be talking about ALMA studies looking at the CGM. And a couple of these have been done by Seiji Fujimoto, where he looked at a stack of galaxies between redshift 5 and 7, and then a single galaxies from the Alpine survey, again at redshift 4 to 6, and looked at the radial brightness profiles of these galaxies with different tracers. So this radial brightness profiles, y-axis is intensity, x-axis is radius, and you're pretty much looking at the distribution of flux in concentric circular rings and seeing how that changes with radius. So here in the top panel, these were all convolved to a common PSF. And we have 3 different tracers here. Green is the rest frame far infrared, which is tracing the warm dust and the obscured star formation. The blue is the rest frame UV, which traces the stellar distribution. Then the red is the C2 158 micron, which traces multiple phases of gas, both warm and cold, neutral and ionized, and it's just a pretty great tracer of general gas distribution. You can see that the green points lie on the PSF pretty much exactly, which suggests that this is a unresolved, compact dust component. The blue points extend slightly farther out, suggesting that the stars extend beyond the dust. And then the C2 not only extends beyond that, but has a change in slope at high radii, which suggests that there's gas in the inner galaxy and then more gas extending beyond. So this is evidence for a CG, or the detection of the CGM at high redshift. And then in one of the examples from the Alpine study, again, we see that the red C2 points extend beyond the blue stellar and the PSF. So the reasons why the C2 halo could exist are many. And the one I want to point out is it could be possibly satellite galaxies that we're just averaging over when we're doing these radial profiles. I just want to note that if we do see these satellite galaxies, we expect to see the same sort of halo signature in the rest frame UV, which we do not, suggesting this is probably not likely. It's more likely that we're seeing the actual diffuse CGM illuminated by the central galaxy, or inflows or outflows. So in these studies by Seiji, basically they detected gaseous halos around redshift 4 to 6 main sequence star-forming galaxies with C2, And in our study, we wanted to look at a slightly different question, whether we could detect similar halos around AGN host galaxies at cosmic noon with CO. So we need a different sample. We can't use Alpine or the very high redshift galaxies. So we chose the Supersample, which is a Symphony large program. There have been 6 papers out so far, all pretty nice. So Super looked at 39 X-ray selected AGN at cosmic noon. All of them were in well-studied fields with lots of ancillary data. So they're able to make sure that most of these galaxies, the host galaxies of the AGN, lie on the star-forming main sequence. And also they detected evidence for outflows in C4 and O3. They were also looked at with ALMA in 2 different programs. And in a paper by Chiara Tracosta, they analyzed the CO3-2 observations of these 28 galaxies and found that they had 11 detections. And in this paper, they took the integrated CO luminosity, the integrated far infrared luminosity of these AGN host galaxies and compared them with a representative comparison sample of star-forming galaxies at a similar redshift from the FIBS survey, and found that the AGN host galaxies were relatively gas poor, which is a really cool result. But I just want to note that this was done on an integrating over the entire area, and we want to look at the actual morphology of the CO observations. So we need to see what sort of sample we can use. So we looked at the archive for these 2 ALMA observation programs, and we found that there were 28 galaxies that were observed. Of course, we're not going to include the 17 galaxies that were not detected in CO. Since we're looking for CO halos, we do need a bright central source. We also exclude 3 sources that have nearby companions, since we really don't want to include satellite galaxies or mergers. And that leaves us with 8 sources. And we could look at the CO morphologies of each of these galaxies individually, but since we're looking for a low-level emission, we decided to stack them together. A nice thing about ALMA is that you get data cubes for spectral line observations. So we stacked in 3D. We stacked each data cube by taking the values in each data cube, accounting for the different velocity bins, and then looking at 4 different weighting schemes. The first being just general averaging, the second being normalization. We also weighted by inverse variance so that those with lower RMS noise values were weighted higher, and then combining the normalization and the inverse variance. So with these 4 weighting schemes, we created 4 stacked data cubes, and then we used in-moments to collapse these 4 data cubes over 5 velocity bins. So this created 20 different moment zero maps that we could analyze. So this is an example for one of these moment zero maps, where we see the moment zero map on the left, where the contours start at 2 sigma. So we do have a 3 sigma extension to the north, very bright detection in the center. If we take a radial profile of this moment zero map, we get these red points on the right. If we then do a radial profile for the PSF, where the PSF is derived by stacking each of the synthesized beams of the cubes in the same way that we stack the actual data. So it is actually a representative PSF. Then we get this blue line. And then just for, just to show the general noise level, we have a shaded region that shows half of the RMS noise level of the moment zero map. So if all of these red points lay on the line, we would have an unresolved source. But what we see is that the red points have a shallower slope, suggesting that we have some sort of extension. As I mentioned, we don't only have one of these moment zero maps, we have 20. So these show a whole lot of different behaviors. Some of them are definitely point source, but most of them do have these nice extensions. And we decided to take the combined inverse variance normalization weighted data cube with the smallest velocity bin, because that showed the nicest deviation. But this is all pretty quantitative. We wanted to make it a little bit more qualitative. So we analyzed this with a model that we created, a pretty simple one where we start with a 2D circular Gaussian with some known intrinsic full width half max. We convolve this with the PSF of our moment zero map, which results in a convolved model. We then calculate the radial profile of this convolved model, and we compare this radial profile with that of the observed moment zero map. And we use the Bayesian inference code by multinest to find the full width half max of the intrinsic model, such that the radial profiles of the model and the data agree. We also do this for a slightly more complicated model, where instead of a single 2D Gaussian, we have two 2D Gaussians, or a two-component model, each with a different full width half max, and then a third variable of the relative amplitude of the two. So when we try and fit our observed radial profile with a single component, such as a single 2D Gaussian, this is what we get, where again, the red points are the observed moment zero radial profile and the blue is the PSF. Now the best fit intrinsic model is in black and the best fit convolved model is in magenta. If this was a perfect fit, the magenta and red would line up, but there is some disagreement, which is shown in the green residuals. If we now include two components, then they line up much better. Residuals are much lower, but the two-component model includes two more variables. We have to make sure that we're not overfitting. And we do this by calculating a reduced chi-squared, which is smaller for the two-component model, suggesting that we're not overfitting. And I just do want to note that we don't have enough data points to do a BIC or an AIC, but the reduced chi-squared is pretty suggestive. So yeah, both of those suggest that the two-component model is what we are seeing here. And if we have a bright compact component and a diffuse weaker component, that is suggestive of a compact galaxy surrounded by the CGM. So as I mentioned before, we also need to look at the stellar distribution to make sure that we're not seeing satellites. So for these super galaxies, we have a whole lot of HST I-band images. So we stacked 21 of them, extracted a radial profile. We do see some sort of bump, but the emission of this stacked I-band image only extends to 5 kiloparsecs and does not extend to 10 or 15 kiloparsecs like we do in the CO emission. So this suggests that the CO emission is truly the CGM and not the ISM. We can also split this into narrow line and broad line AGN, where we see the same general behavior. So again, this suggests that what we're seeing in the CO is truly the CGM rather than the ISM. So we can test our model on different data just to make sure that we're not making CGM out of nothing. So we can look at a few of the Alpine sources. So Alpine is a different sort of sample. Instead of redshift 2 AGN and CO, it's redshift 4 to 6 star-forming galaxies at C2. But in the paper by Seiji, they did find evidence for these extended halos. When we we downloaded this data from the Alpine archive and extracted a radial profile, fit it with a single component, and found that if we have a single component with a radius of around 1 to 2 kiloparsecs, that exactly duplicates the observed radial profile, suggesting that there's no halo, it's just extended resolved emission. And this is true for all 8 of the galaxies that were claimed to have extended emission in Alpine. They all have radii between 1 and 3 kiloparsecs, no need for a second diffuse component. So this raises one of the main points, which is there's an issue of terminology, because all of these Alpine sources have extended C2 emission that is resolved, but we believe that we're just looking at the ISM, and we're not looking at the C2, the halo, or the CGM, or any diffuse emission. So, so just to conclude, we used some archival CO3-2 observations of the Super ALMA survey to find evidence for diffuse CO emission around these AGN host galaxies at cosmic noon. And we confirmed that this is not replicated in the HST images. And then we tested our technique on some Alpine data and found that in those cases, there's no significant evidence from our analysis of a diffuse halo. So in the future, we're going to extend this to other galaxies at intermediate redshift and look at the much more extended emission with ACA data. So thank you.
Well, thank you very much, Gareth, for this presentation. I saw that there are plenty of questions already in the chat, but I will take the first question. Have you thought before to use visibility data to make the stacking rather than to stack images?
Yes, so that is, yeah, that would be, I guess not easier, but that would be the better way to do things. And there's someone else at Cambridge who's actually doing that right now. Jan Schultz is running a visibility stack on the CO and C1 data for extremely red quasars at the same redshift. So in the future, we might extend that analysis to this data as well.
There are some tools around, so we can discuss later, but there are some tools to do this on.
Right. Thanks.
We can take the questions from the chat, maybe.
Yeah, so there's actually another question on the stacking. Wouldn't you expect to only detect extensions if they're aligned in the same direction?
Yeah, so the idea behind our stacking and the stacking of the PSFs was that if the extensions were biconical, and if we stack 8 of them, they should have random orientations, and so the evidence of the halo should be more or less isotropic, which is why we assumed a circular 2D Gaussian rather than trying to go for some inclined Circic profile. So in reality, each of them probably does have some, complex morphology and extension, but with the stacking, we are trying to account for that. That's a good point. Thank you.
Okay. And there's another question, which line can be best used to trace this CGM mass for these high Z systems?
Ooh, that is a tricky point. So with the CO, you would have to assume a conversion factor back to CO 1 to 0, and then you would have to assume an alpha CO, but alpha CO varies by order of magnitude within a galaxy. So when you get to the CGM, that's going to be trickier. There have been a lot of really nice results using C2 as a molecular gas tracer, but that's been inside galaxies. And even though it's been in both starburst and main sequence galaxies, the extension to diffuse gas is tricky. And C1 has similar issues to CO. So a combination of all of them, maybe, and the continuum.
Okay, great, thanks. There's, there's another question actually, sorry. Do you think the existence of gaseous halos is due to the AGN, since you do not find C+ halo in Alpine sources?
Yes, so it's, I'm gonna see if I can share for another few seconds, sorry. So we actually did look, so we do think that the AGN would have a stronger outflow than the starburst activity, and even then, not really starburst, the star supernova activity of these galaxies. But we did also run our tests on the high resolution C2 observations of HC4, which was one of the Alpine sources. And we found that if in this higher resolution observation, there is actually evidence for a very strong diffuse component. And you would need a much more complex model. So we think that it's a combination of main sequence versus AGN, but also it's important to take the resolution into account. Since for the starburst galaxies, the compact galaxy must be much more compact.
Great, thanks.
Okay, thank you again, Gareth. Thanks again to all the speakers of the session.